We present the results of a high reliability, latency bounded conveyor belt control system for a cart containing a self-localizing wireless sensor node. The rise of the industrial Internet of Things has been and will continue to be driven by the availability of wireless sensor networks, embedded systems, and inexpensive sensors. Wireless sensor and actuator networks could also enable wireless control and factory automation, taking advantage of the benefits of wireless communication for control. Low latency, high reliability networks are of paramount importance for successful automation of wireless factory robots. For many mobile systems, location information and tracking greatly improves the quality and utility of the data and is vital for them to perform intelligent tasks in industrial environments. This is especially true for wireless industrial control, where position feedback can be critical for the use of the system. RFID has shown promise in tracking assets throughout production, but lacks the reliability or the accuracy to be suitable for control applications. Lighthouse positional tracking, a localization system that uses a temporally structured infrared illumination scheme generated by a set of base stations to convey position information, is another technology that has shown high precision in industrial applications. For instance, Nikon's large-scale metrology system, IGPS, advertises 200 micrometer precision. On the other hand, HTC Vive, a consumer virtual reality headset and corresponding Lighthouse motion capture system, has also been gaining significant attention as a cost-effective, high-precision post-tracking system that uses a method similar to angle of arrival and advertises millimeter precision. The HTC Vive Lighthouse uses line-generating optics to perform planar laser sweeps of infrared light across the tracking range. Once the rotating laser reaches a reference bearing, an array of wide-angle LEDs flash for a specified amount of time to sync the timers of all the nodes in the tracking range and communicate via the duration of the pulse the axis, horizontal or vertical, on which the rotating laser is sweeping. Once the planar laser sweep hits the photodiode mounted on the track node converts the time difference between the sweep hit and the original sync pulse into an azimuth or elevation angle relative to the reference bearing in the Lighthouse base station's reference frame. Our work focuses on using a miniature wireless inertial sensor mode to implement a low latency, high precision, high reliability, state estimation, and wireless control system for tracking the position of objects in industrial settings. The reduced size and cost of the measurement system makes it more amenable to large-scale implementation. Previously, Schindler et al. Demonstrated performing this task using the As-built HP model photoelectric sensors placed adjacent to the conveyor belt as beam breakers to sense when the cart has reached an unsafe zone boundary on the conveyor belt. Once the beam breakers detect the cart, they trigger an interrupt on an attached transmitting wireless sensor node, which sends a wireless signal to the motor controller to change the direction of the conveyor belt. Their implementation, as with ours, takes advantage of a high reliability, low latency communication protocol for the IEEE 802.15.4 standard with multiple low-cost modes, channel frequency diversity, and transmission redundancy. This ensures low transmission latency and a high packet delivery ratio to provide the system with a high level of reliability in an industrial environment. Our implementation, shown in this slide, uses an extended Kalman filter, or an EKF, running on board a wireless sensor node on the cart for position and velocity estimation using both inertial measurements and Lighthouse localization. We show that the EKF provides equivalent response latency to the as-built sensors when the cart reaches an unsafe zone boundary. We also show that the EKF enables high reliability control with strong tolerance to occlusion from external mounted sensors like the Lighthouse. Conversely, the as-built photoelectric sensors used in Schindler et al.'s system provide no occlusion to tolerance or state estimation, as they can only rely on a single measurement from the sensor and would not be able to predict when the object would cross the conveyor belt's boundary into an unsafe zone. The core of the latency-bounded, high-reliability wireless localization and conveyor belt motor control system is the micro-inertial measurement system, or MIMSI, an open-source wireless sensor mode containing an ARM Cortex-M3 microprocessor, an InvenSense MPU 9250 9-axis IMU, and an 802.15.4 transceiver. The conveyor belt wireless control setup shown in the figure, contains a DC regulated power supply, 2 receiving MIMSIs attached to an Arduino Uno controlling a DC motor. Across from the conveyor belt, an HTC Vive Lighthouse base station 3 meters away, and a transmitting MIMSI on the cart powered by a LiPo battery equipped with an MPU 9250 9-axis IMU and attached to a TS3633 CM1 integrated circuit and infrared sensitive photodiode for picking up pulse train envelopes from the Lighthouse base station. Using the unofficial documentation on Vive's base station and its communication protocols available on GitHub, we were able to write custom firmware on top of the existing low latency, high reliability communication firmware, allowing MIMSI to localize itself on the conveyor belt relative to the Lighthouse. The TS3633CM1 prototyping module is an integrated circuit and photodiode that generates an envelope pulse train of the infrared signals received from the Lighthouse, which the MIMSI receives as rising and falling edges through its GPIO pins. The written firmware uses rising and falling edge hardware capture registers to record pulse timings precise to 100 nanoseconds, in addition to falling edge interrupts to read from those registers and decode the pulse trains as horizontal and vertical angle information. The transmitting MIMSI on the cart updates the cart's position and velocity estimate on the conveyor belt via an extended Kalman filter, taking acceleration data given by MIMSI's onboard IMU in addition to azimuth data from the Lighthouse generated from the aforementioned hardware capture register and interrupt scheme. As the transmitting MIMSI approaches a given edge of the cart, it sends several redundant packets on two different channels, 16 and 20, indicating proximity to the edge of the conveyor belt. The receiving MIMSIs receive these packets and send a signal over GPIO pins, notifying the motor controller to change the direction of the conveyor belt such that the cart doesn't enter the unsafe zone shown in the previous figure. As in Schindler et al.'s implementation with the as-built photoelectric sensors, mesh networking or TISH capabilities of OpenWSN were not used in this system. However, it did build upon the open source OpenWSN board support package for the CT2538 system on chip, or SoC, which provides an abstraction of the underlying hardware. Additionally, taking advantage of this lower level network control allows for reduced latency when compared to the full OpenWSN stack implementation, at the expense of higher power consumption and limited networking functionality. All relevant low latency, Lighthouse localization, and state estimation firmware written for MIMSI can be found on GitHub. Taking advantage of a diverse set of sensors under a Bayesian state estimation scheme directly increases both the reliability and the tracking accuracy of our system, simultaneously reducing the response latency of control updates. Because of the weak nonlinearity introduced by the angle to position mapping in our localization system, we used an extended Kalman filter to combine accelerometer measurements from the MPU 950 IMU with Lighthouse azimuth measurements. The dynamics used for state estimation are shown on the top left. The system states are cart position x of k and cart velocity v of k. The input is the acceleration measured from the IMU, which consists of the true acceleration a and additive noise na, with zero mean and variance sigma squared a. The acceleration is sampled with period delta ta. The measurement model is shown on the top right, with the measurement z of k being equal to the sum of the true horizontal angle phi of k, calculated from the arctan of the position divided by the distance from the Lighthouse to the belt, to the cart, and the corresponding Jacobian is shown below. In each step of the extended Kalman filter, we predict the next state by a dynamics model and corresponding Jacobian matrix, and we then predict our state covariance with process noise covariances shown in the bottom left. Given a new measurement, the next step is to compute the innovation from said measurement and then the Kalman gain from our state covariance and the Jacobian of our measurement model and our measurement covariance. All of that is shown in the bottom right. Then in the next step, we update our state estimate as shown in the far bottom right, and then update our state covariance. Our state covariances are used when quantifying the performance of the extended Kalman filter when it comes to tolerance to occlusion. As another note, for monitoring network latency, a computer running a custom Python test harness and an analog discovery tool were used. Over 10,000 packets sent, as shown in Schindler et al.'s implementation. The maximum latency was 1.6 milliseconds and the minimum communication latency was 0.8 milliseconds, with all 10,000 packets received by the receiving modes, demonstrating low latency and high reliability in the networking protocol. As an initial metric of the Lighthouse measurement system's reliability, and in order to quantify the precision of the accelerometer and Lighthouse measurements in the extended Kalman filter, we quantified the precision of the Lighthouse horizontal angle measurements on a MIMSI using the hardware capture register and interrupt scheme for capturing infrared pulses and sweeps. The distribution of 1 million Lighthouse measurements taken reports a standard deviation of 35 microradians, equivalent to 100 microns or 0.1 millimeters, with a base station at a distance of 3 meters away. Additionally, we see 0 outliers outside of the plus or minus 1 millimeter error range at 3 meters away over 1 million measurements, further reinforcing the precision and reliability of this lighthouse localization system. On the right, we show the x-axis acceleration of the measured by the MIMSY's IMU, which shows when the cart switches directions, its maximum magnitude of acceleration is roughly 2 Gs. At an update rate of 1 kilohertz, the resting baseline standard deviation is roughly a tenth of a meter per second squared, which we use in the extended Kalman filter. Using the extended Kalman filter allows us to take advantage of all previous position measurements from the lighthouse, using the accelerometer to predict the state in between lighthouse measurement updates for a continuously updating position velocity estimate, mitigating any issues with the system's response latency brought on by the lighthouse's mere 60 hertz update rate. This figure shows how the use of the EKF improves the response latency of the wireless control system by continuously predicting the position and velocity states of the cart between updates from the lighthouse sensor. This implementation, updating at a 1 kilohertz accelerometer update rate, enables a median response latency of 3 milliseconds, which is a significant improvement on the nearly 30 millisecond response latency when using lighthouse measurements alone, in absence of the accelerometer data. This is equivalent to the response latency of the 1 to 3 millisecond latency of the as-built HP model photoelectric sensors used in Schindler et al.'s implementation. And this can be further improved by upping the update rate of the accelerometer. As with the photoelectric sensors used in Schindler et al., the use of Lighthouse alone provides no tolerance to occlusion on its own, since Lighthouse measurements are not received on the Lighthouse base station emitter as occluded from the photodiode on the transmitting MIMSY. In the case that occlusion occurs at a boundary of an unsafe zone, the transmitting MIMSY, whether in Schindler et al.'s implementation or in ours with Lighthouse alone, will be unaware that it has reached the boundary and will enter the unsafe zone without sending a wireless control signal. Accelerometers alone, on the other hand, are known for producing notably poor translation estimates for dead reckoning over long periods of time due to scale factors and bias drift. However, in our EKF implementation, information from all previous lighthouse measurements are propagated into future states even once occluded, such that the accelerometer can be successfully used to perform precise positional tracking while occluded from the lighthouse base station. We performed a set of experiments where we occluded the entire left half of the conveyor belt, including the unsafe zone boundary, from the lighthouse base station in order to analyze our system's tolerance to occlusion. This figure shows the results of this experiment, displaying the EKF position estimate variance distributions over several cycles back and forth across the belt. When no part of the conveyor belt is occluded from the lighthouse base station, we see an expected 0.1 millimeter median standard deviation. However, when half of the conveyor belt is occluded from the base station, the EKF reports a median position estimate standard deviation at the occluded boundary of still less than 1 millimeter, even after 10 centimeters of occlusion on the belt moving at a high velocity, indicating high tolerance to occlusion and, by extension, significant additional reliability in our system. Though for this work, we use the micro-inertial measurement system as the wireless sensor node at the core of this inertial wireless control system, inertial lighthouse wireless control system. This system is directly compatible with a monolithic wireless system on chip that requires no external components, known as the single chip micromote, or SCUM. SCUM contains an ARM Cortex M0 microprocessor and a 2.4 gigahertz radio compatible with Bluetooth Low Energy, or BLE, and the IEEE 802.15.4 standard. The latter allowing us to implement the same exact low latency board support package implemented for the transmitting MIMSYs to communicate to the receiving modes. SCUM additionally contains an optical receiver whose primary function is actually for optical bootloading. Additionally, this same optical receiver is also able to detect the infrared pulses emitted by the HTC Vive Lighthouse base stations in order to localize itself, and has been shown to achieve centimeter precision localization in a 2-lighthouse system. Future work could additionally investigate compatibility with Nikon's large-scale metrology IGPS system. This single-chip micromote will enable such cubic millimeter sensor modes to act as low-cost markers for wireless industrial control systems, in addition to a slew of other applications in the realm of localization, wireless sensor networks, and the realization of Industry 4.0. Thank you.